Welcome to SciFlux. Here you get daily coverage of the latest scientific research. Every day, we bring you new research in a clear and simple format so you can stay informed without wasting time. Like the video, subscribe, and leave a comment to stay connected and help this channel grow. And if you want each new research delivered directly to you, join the SciFlux newsletter. This study investigates the resilience of directed networks by extending fundamental graph theory results to complex, real-world systems. Building on the Nash-Williams and Tutti theorem, which specifies when an undirected graph can be decomposed into Ki edge disjoint spanning trees. Researchers Fang and Yang explored what happens when a graph exceeds the minimum density for K trees, revealing that an additional, large forest of connections emerges. The current research adapts these concepts to directed graphs, where the equivalent of a spanning tree is a spanning arborescence. By reformulating density and connectivity measures for directed edges, the team proved that sufficiently dense digraphs contain Ka edge disjoint spanning arborescences plus an extra, large forest-like structure, significantly enhancing redundancy and connectivity. These results provide critical insights into network architecture, offering practical implications for designing robust communication systems, optimizing traffic flow, and understanding dependencies in biological networks. This digraphic extension represents a major step toward predicting and ensuring fault-tolerant connectivity in complex directed networks. This research investigates the structure of multi-signed complete graphs, where every node in a network connects to every other node, and each connection carries a vector of binary values or a multi-sign. The study focuses on Hamiltonian circles, loops that visit every node exactly once, and calculates the cumulative multisign along these paths using a special binary arithmetic. The key finding is that for networks with a sufficiently large number of nodes, the set of all multisigns generated by Hamiltonian circles consistently forms one of three structured mathematical types: a subspace, an affine subspace, or the full vector space of all possible binary strings, with a few exceptional cases. This reveals an unexpected algebraic order within highly complex networks. These results provide a robust framework for analyzing information flow in networks where connections carry multiple data layers. Applications range from secure communication and cryptography to systems biology, where multi-signs can represent states of metabolic pathways. By uncovering predictable patterns in otherwise intricate systems, this study offers new insights for designing more resilient and efficient network architectures. This research investigates long-standing problems in group theory, specifically Anderson's conjecture on symmetric sequencings and Bailey's conjecture on two-sequencings. These conjectures address how elements in mathematical groups can be systematically ordered, revealing fundamental insights into group structure. The study focuses on sufficiently large groups using rigorous combinatorial analysis and examining partial sequences, including harmonious and R-sequencings, to understand their extension potential. The findings confirm that both conjectures hold true for large groups. Additionally, the researchers explored double sequencings, detailing their properties across both abelian groups, where operations commute, and non-abelian groups, where the order of operations is critical. This work fills key gaps in abstract algebra and combinatorics, providing new frameworks for understanding the structure of mathematical groups. Its implications extend beyond pure mathematics, informing fields such as crystallography, particle physics, cryptography, and computer algorithms. By uncovering predictable patterns within complex structures, this research enhances our comprehension of the fundamental order underlying diverse systems. This research investigates alternating sign formulas for Eulerian numbers, a fundamental sequence with applications in combinatorics, probability, and computer science. Eulerian numbers count permutations with a specific number of ascents and possess rich structural properties, including elegant alternating sign expressions. The study rigorously confirms two such formulas using the D.I.E method: description, involution, enumeration. Central to this method is a sign-reversing involution, a systematic pairing of terms with opposite signs that cancel, leaving only the unpaired contributions that yield the simplified formula. By carefully constructing these involutions, the researchers demonstrated precise cancellations, validating the alternating sign identities for Eulerian numbers. Beyond these specific formulas, the work provides a generalizable framework. The D.I.E constructions developed here can be adapted to prove a wide range of complex combinatorial identities, offering a powerful tool for uncovering hidden patterns and relationships across mathematics. This study highlights how structured, elegant methods not only confirm known results, but open new avenues for exploration in combinatorial theory. This research investigates the complex Monge Ampère equation, a central, highly nonlinear problem in complex geometry with links to pluripotential theory, analysis, and theoretical physics. Understanding its Hölder continuous solutions, smoother than continuous but not necessarily differentiable, has been a long-standing challenge. Focusing on bounded domains in n-dimensional complex space, the study establishes a necessary and sufficient condition for the existence of these solutions. If the condition holds, a solution exists. If a solution exists, the condition must hold. This definitive if and only if result fully characterizes when Hölder solutions occur. The research also refines knowledge of solution regularity on general B-regular domains, deepening understanding of how solutions behave. This work is a foundational advance, providing a clear roadmap for future research and simplifying a previously complex landscape, with implications across both pure and applied mathematics. This research explores the Bohr phenomenon in complex analysis, extending it from classical power series to holomorphic mappings in Banach spaces. The original Bohr inequality bounds the sum of a series' coefficient magnitudes within a specific radius. This study examines whether similar constraints hold in higher dimensional, more complex settings. The team analyzed mappings through their homogeneous expansions, examining norms and squared norms of coefficients, and achieved three main results: an improved Bohr inequality using squared norms for tighter bounds, a refined inequality combining absolute values and squared norms of coefficients, extension to composed functions, especially Schwartz mappings with zeros of a given order, with all inequalities having sharp Bohr radii. These findings provide precise bounds for complex functions, offering essential tools for functional analysis, operator theory, and theoretical physics, and deepen our understanding of high-dimensional complex mappings and their inherent structure. This research bridges discrete holomorphic iteration and continuous semigroups of holomorphic functions, revealing the long-term behavior of complex systems in the unit disk. Traditionally, discrete iteration, repeatedly applying a function to generate a sequence of points, and continuous semigroup theory have been treated separately. Connecting them allows for a precise understanding of asymptotic behavior in complex dynamics. The team developed a semigroupification technique, embedding discrete orbits into continuous flows, extending previous methods to a wider class of functions, including non-univalent ones. This approach transforms step-by-step sequences into smooth, predictive trajectories. Key results include sharp estimates for the convergence rate of orbits to their attracting fixed points, precise evaluation of orbit slopes, showing they behave like quasi-geodesic curves during non-tangential convergence. This framework unifies discrete and continuous perspectives, offering powerful analytical tools to study complex dynamical systems and uncovering the continuous order underlying seemingly chaotic discrete processes. This research explores hyperkähler manifolds of infinite topological type, extending classical work by Claude Lebrun on finite configurations. These four-dimensional spaces, vital in theoretical physics and geometry, are built using the Gibbons-Hawking ansatz, which arranges monopoles, point-like geometric charges that dictate the manifold's structure. Two key scenarios were studied: a generic case with well-separated monopoles and a clumped case with clustered monopoles. In the generic scenario, the infinitely complex manifold is biholomorphic to a hypersurface in three-dimensional complex space, described by an explicit, elegant function valid for almost all interpretations. In the clumped scenario, potential singularities arise, but the manifold remains biholomorphic to a minimal resolution of a singular surface, a smoothed version of the irregular space. By providing explicit, concrete descriptions, this work significantly advances understanding of infinite hyperkähler geometries, extending Lebrun's foundational results. It illuminates the hidden structure of these exotic spaces and offers tools potentially impactful for both pure mathematics and theoretical physics, revealing deeper insights into complex geometric structures that underpin the universe. Thanks for watching. If you enjoyed the video, please like, comment, and subscribe. Also, join our newsletter to stay informed with the latest discoveries shaping science and innovation. See you tomorrow with a new round of breakthroughs. Take care.